This video covers Section 2 of Chapter 5 on relationships between two categorical variables. We'll talk about constructing and using two-way tables, summarizing and displaying relationships between two variables, comparing proportions or counts in two categorical variables, and we'll take a look at confounding variables. Of the 4 stages of statistics, this lecture will cover displaying and summarizing relationships between two categorical variables. Recall that we display and summarize categorical variables using either a pie chart or bar graph for the display and the count, proportion, or percentage for summaries. When we add a categorical explanatory variable, we will simply extend each of these display and summary methods. In particular, we'll focus on using bar graphs for the display and on proportion or percentage for summaries. Let's look at an example. In the student survey data, we see this relationship between gender and lens wear, contacts, glasses, or none. The relationship is currently displayed in a two-way table, which I'll show you how to generate in a few minutes. Looking at this table, how do we read it? What part of the table gives us information about the individual variables, not the relationship, but the individual variables, gender and lens wear? The rows correspond to gender, the columns correspond to lens wear. So for gender, the information that we can that we'd like about how many of each gender there are can be found in the total column over on the far right. The bottom row gives the totals for each type of lens wear. With the same table, what part of the table gives us information about the relationship, which is what we're focused on in this lecture? It's the numbers in the middle that give us the information about the relationship we're looking for. Let's take a look at how to generate that two-way table that we've just been looking at. Here's our student survey data. We're looking for the relationship between sex and lens wear. So let's start by copying the column for sex or gender. I'm going to add that into a new sheet. So let's paste that in. There we go. And now let's go back to the survey data and let's find the column for lens wear. There we go. It's labeled eyes here. CL is contact lenses, N is none, EG is eyeglasses. So let's copy that, go back over to our other sheet, and we'll paste it in right next door. Now, we're ready to generate our two-way table. We do that with a pivot table, so let's go to the Insert tab, and I'll select Pivot Table. First, where is our data? I'll click the little box here, and I'm going to select columns A and B because we want both. I want the pivot table to go in the existing worksheet, and it's actually already selected one cell. I'm going to move it up just a little bit. We'll put it there, and I'll click OK. And now we are ready to go with our table. The table that we just saw had gender on the labeling the rows. So I'm going to take sex and drag it down here to rows. Come on. There we go. I clicked the little box next to it and it appeared. But you need to make sure that sex gets dragged down here to rows. And now I need eyes. I want eyes on the column, so I'm going to drag eyes to columns. And now what do we want in the value fields? Generally what you want to put there is the same thing as you just dragged to columns. So I'm going to drag eyes down to values as well, and it should automatically go to count. Let me make this just a little bit bigger, maybe so you can see it a little better. Okay. I don't need these the column and the rows for blank, so next to sex, I'm going to click the little bar there and I'm going to uncheck blank. And next to eyes, I'm going to do the same thing. I'm going to uncheck blank. And now this is the same table we just saw a moment ago. It's just that easy. Before we move on, we need a quick definition. A conditional percentage or conditional proportion is the number that we're going to use to make comparisons when we're looking at relationships between two categorical variables. To compute these percentages or proportions, we start by looking at only the respondents to the survey or only the individuals in the study that fall into a particular category in the explanatory variable. Within that subset of our sample, we'll look at the percentages that fall in each response value. Whenever we see the word conditional, and we'll see it in several different contexts in this course, you should associate that word with the phrase, given that. We will see that several times. So let's take a look at an example from our two-way table that we've been considering. Notice that 129 of the females and 85 of the males reported none for lenses. Should we make the claim that fewer males wore no lenses? But using counts can be misleading because the total values, in other words, the total number of females and the total number of males, is different. So looking at the raw numbers, those counts, isn't good enough. Instead, we need to look at the conditional proportions or conditional percentages. For females, we divide 129 by 282, and that gives us 46%. For men, we divide the 85 by 164, and we get 52%. So in fact, the proportion of males with no lens wear is higher. Going back to the pivot table we created a moment ago, how can we report, instead of counts, these conditional proportions? To do so, let's go back down to the bottom right corner where we entered the values. Notice right now it says count of eyes. We don't want the count, we want a proportion. So let's click on the little arrow next to it and then select value field settings. Right now it's on count of eyes, and count is selected here. To change it to a percentage or proportion, go to the tab that says Show Values As. Right now it says no calculation, but click in the little box there, and we get several options. Let me move this out of the way so we can see. What we want to report is the percentage of the total of each within each gender. So we want this reported as a percentage of the row total. Now you see that each row adds up to 100%. And here we see the numbers that we saw earlier. For males, it's 52% have no lenses. For females, it's 46%. If there are too many decimals here, more than you want, you can highlight the columns, and up here, we're in the Home tab, you can see buttons for increasing or decreasing the number of decimals. So once we have our information about the conditional proportions how do we display the relationship? The best way is with a bar chart. Since sex represents our explanatory variable, it will go on the horizontal axis, and the percentage or proportion, your choice, for the lenses will go on the vertical axis. So since about 43% of females wear contacts, above female will make the bar corresponding with contacts have a height of 43. Looking at the other conditional percentages, we'll fill in the heights of the other bars in the corresponding way. There's another option here. We could also show three groups with 2 bars each. In other words, put the 2 bars for contacts next to each other so that they're easier to compare. Similarly, put the 2 bars for glasses next to each other so they're easier to compare. And put the 2 bars for none next to each other so they're easier to compare. We can use Excel to generate a bar chart just like the one we saw. Again, looking back at our pivot table with the conditional proportions listed here, how do we get the bar chart? If you look up at the top here, when I've got one of the cells inside the pivot table selected, you should see some pivot table tools. You can't quite see here off the top of the recording where mine says pivot table tools, but I see Analyze and Design right next to it. So I'm going to click on Analyze, and you see some information about the pivot table here. One of the things that I see over to the side is a pivot chart. This is the easiest way to get the bar chart that you need. Click on Pivot Chart and Clustered Column. And there is our chart. Female and male on the horizontal axis, and then the different possible values for eyes in the right proportions on the vertical axis. Another display type that you might see with 2 or more possible values for the explanatory categorical variable is a mosaic display. Here we have a big square that contains all of our data. The top portion of the square, not the top half, but the top portion, represents the females. It's a little bit taller because there are more females than males. The relative heights of these 2 pieces of the square give you the relative sizes of those 2 groups in the sample. Within each of those rectangles, the one for the females and the one for the males, we have 3 different smaller rectangles, each one representing one of the response values. Contacts in number 1, glasses in number 2, no lenses at all in number 3. So let's take a look at interpreting what we found. Looking at the counts and the conditional percentages that we can get from our pivot table, the question that we'd like to answer is, are you convinced that, in general, all females wear contacts more than males do? And that all males are more likely to wear no lenses than all females? To talk about how convinced we are, we should look at how different these percentages really are. For contacts, the 43% for women seems much higher than the 26% for men. whereas the difference in the percentages for known lenses, 46 to 52, seems pretty close. This is really a question of inference when we're going from a sample to the population. Later on in the term, we'll look at how to use the sample size to put a numerical value on the difference between these two percentages and use that to decide whether our evidence is convincing. Let's take a look at a different example. An experiment considered if wasp larvae were less likely to attack an embryo if it was a brother. What should we be looking at in this table? Here the explanatory variable is brother or unrelated, and the response variable is attacked or not attacked. So we're interested in looking at the proportions. For brother, 52% were attacked, and for unrelated, where 77% were attacked. We see that unrelated embryos were more likely to be attacked. Here's another comparison we may wish to consider when we're looking at relationships between two categorical variables. Instead of looking at how different the proportions are in a two-way table, if we want to consider counts, what we might want to compare is how different the actual counts are from what we would call the expected counts. It's that question of expectation that's interesting. So let's take a look at how to find this table of expected counts. So in the wasp example, what would the expected counts be? Well, when we're creating the table of expected counts, what we're looking at is what would the counts be if there were absolutely no relationship between the two variables? Overall, 40 out of the 62 get attacked. So if there were no relationship between the variables, we would expect that 40 out of 62, which reduces to 20 out of 31, would be attacked no matter what the value is for the relationship. So since 40 out of 62 is the same thing as 20 over 31, we would expect 20 out of the 31 brothers to be attacked and 20 out of the 31 unrelateds to be attacked. That means the other 11 would be not attacked in each group. Notice the fact that this was an experiment, so the individuals were evenly divided between brother and unrelated. The fact that we had 31 in each group, the fact that those numbers are the same makes this calculation a little bit easier. In a moment, we'll look at how to do this calculation if those numbers are not the same. But first, let's look at the WASP example one more time. On the left, we see the observed table with columns corresponding to attacked and not attacked. The rows are brother and unrelated. The T's represent totals. On the left, we see the observed values in the experiment. On the right, we see the expected values that we just calculated. How do these compare? Notice that each observed value is either 4 more or 4 less than what we see in the expected table. When we get to inference later on in the term, we will be able to measure the size of these differences in a way that lets us know if our evidence is strong enough to conclude a relationship between the variables. Now let's take a look at the expected counts in our lenswear table, in which the rows did not have the same totals. How do we find these expected counts? Look at the bottom row for totals in each category for the response variable. we see that the proportion of people who wear glasses is 69 out of 446. If there was no relationship, we would expect that 69 out of 446, which is the proportion overall that wear glasses, that proportion would hold true within each group. So we would multiply that times the 282 to get the proportion, the count that we would expect to see within the female group. That's 44. And the other 25, which we can find by subtracting, notice the computation down here. If I know that there are 44 in the female and glasses column, that column has to add up to 69, so males with glasses must be 25. Now, that's the theory behind how we get these expected counts. On the next slide, I'll show you how to do this computation quickly. Let's go back to Excel, looking at the eyewear table that we've just created, and let's make a table of expected counts. So the first thing I'm going to do is take the chart that we created and move it out of the way. And I need to take the pivot table that we started with, I need to return that to the original display, which was showing a count. So once again, I'm going to go down to values, where I see the little arrow next to count of expected values. I'm going to go to value field settings. I'm going to go back to show values as, and I'm going to go back and select no calculation. That'll return me to the counts. Now underneath, I'm going to reproduce this table by hand, except I'm going to type expected counts, and then underneath I'll just reproduce everything. Sex, female, male, grand total, and then up here next to sex I'll do contact lenses, eyeglasses, neither, and grand total. Now, when you're looking at a table of expected counts, the total of each row and the total of each column will always be the same. So the grand totals of the rows will always be, the grand total of each column will be equal to, and now notice I'm doing this as a formula in Excel, 163. For the total of eyeglasses, I think in this case it's going to be easier just to type them all in. So this is going to be 69. For neither, it'll be 214. Grand total here is 446. For the male total is 164. And the female total is 282. Now, to get the expected counts, here's what we do. The expected entry in each of these cells will be equal to the product of the total of the column, so the column total times the row total divided by the grand total. If you go back to the previous slide, you'll see that is the computation that we did. Not quite in that order, that's not how we explained it, but that's how we compute it. I'm going to do the same thing for the others. So for males, it'll be the column total times the row total divided by the grand total. Column total times row total over grand total equals column total times row total divided by grand total equals column total times row total over grand total equals column total times row total divided by grand total. You may notice that these are not all whole numbers. In general, they won't be. But since we're talking about counts, we will tend to round these off to the nearest whole number. So to make that happen, I'm going to select those, the numbers that we just got. And up here at the top, under the Home tab, under General, you see this increases the number of decimals and this decreases the number of decimals. I'm going to click Decrease Decimals until we're looking at whole numbers. So here we have our table of expected counts. So looking at this example again, here's our observed values. If gender and lenswear were unrelated, the expected values for glasses would be 44 for females and 25 for males. How different are those? Well, 32 wore glasses as opposed to the expectation of 44, which is quite a bit less compared to what we would expect if there were no relationship. And for the men, we see more wearing glasses than what we would expect. If we're looking at an observational study and we're trying to look for a relationship between two variables using a two-way table, don't forget that we could be dealing with confounding variables. Before you report a relationship between the two variables, consider the sampling and design issues that we've talked about to see if we have accounted for any possible confounding. Let's take a look at an example. Here we see survey results for full-time students. The rows are major, decided or undecided, and the columns are residency status, on campus or off campus. Is there a relationship between whether a major has been chosen and whether a student lives on campus or off campus? But certainly the percentages are different. 60% of undecided majors live on campus, 43% of decided majors live on campus. But is it possible there's a confounding variable? Think about it for a moment. Did you figure it out? The year at school could be a confounding variable because underclassmen are less likely to have declared a major and are also more likely to live on campus. So how do we handle this? One good way to do it is to block the data. Let's separate out the responses according to whether a student is an underclassman or an upperclassman. Now look at the rates of decided versus undecided. Do they look all that different? For underclassmen, it's essentially the same. For upperclassmen, there's a bit more of a difference, 21% to 13% for on-campus. But are you more or less convinced of a relationship between these variables? Once we get to inference, we will show that this difference, this 8% difference, does not reach the level of what we call statistical significance. Simpson's paradox is the name that we put on the following phenomenon that is seen sometimes in data. If you look at an observational study, if the relationship between variables changes based on whether we have separated out groups, whether we have blocked the sample or kept them together, this is called Simpson's paradox. For example, suppose that boys tend to eat a lot of sugar and they also tend to be hyperactive. Girls tend not to eat much sugar and are less likely to be hyperactive. Why would the data here lead to a misperception that sugar causes hyperactivity? Well, this is an example of Simpson's paradox. See what we did there? So, in summary, we looked at creating and using two-way tables to explore relationships between two categorical variables. The individual variables go in the margins, and the relationships inside the table. We'll put the explanatory values as labels for the rows, response as labels for the columns. We talked about summarizing the relationship by comparing the conditional proportions or percentages. We looked at how to create a display using a bar graph, and how to interpret the results by looking at the differences in the proportions. Finally, we looked at creating a table of expected counts to create a different comparison, that between the expected and observed counts. We also talked about the relationship that confounding has with categorical relationships between two variables, and looked at an example.